Hello, everyone. Welcome back to a new episode of Advent of Code 2016. We were, and indeed still are, in the middle of debugging our A-star search for day 11. Well, debugging either our search or our problem statement. Not problem statement, problem modeling. It seems like it would be relatively cheap to just go ahead and implement duplicate removal. So let's go look up in Python implement hash and eq, please. How should I do this? Yes, I did mean hash and eq. Thank you, Google. Here, we'll just close that search. What is a correct and good way to implement them? An easy way is to use a key tuple. Okay, I see. So there, that's one recommendation. Yeah. Okay, that's fine. We can do that. Hello, Python, wake up. So it's kind of a pain, but what we can do is say def key of self to be return basically rooms and elevator. Actually, can I just use vars? And vars? Huh? Then we could have a map and that could get hashed. That seems okay. Just double check class foo. I see that. Okay. Class foo def foo of self to be return vars foo or let's see, x equals foo x dot y equals 1, x dot foo. Yeah, that's fine. No, wait. It doesn't give us a y thing, so vars was not correct. Python object. Oh, vars of self. Right, oops. Yeah, that sounds right. So let's redefine this thing again. Def foo of self to be return vars of self, and then we'll write x equals foo, x dot y is 1. What is x dot foo? It's a map y1, and that has a what? None type? Why is that none type? Why is that map not hashable, please? Hash? Like, what? Dicts are not hashable? What? What is wrong with you, Python? Ugh. Okay, well. Def hash self to be return keys. Yeah, so now you can't use vars. It's got to be return a tuple of self dot rooms and self.elevator dot hash def eq of self other, I assume. Yes. Return self dot. Oh wait, do I have to call self? I forget. Okay, first of all, I typed this like super wrong. It's key. I assume I have to put the self in here. I don't remember. Self dot key equals other dot key. So we can then just copy these 3 lines and paste them into all the classes that we need to do a thing in. We'll have to change the key function for these, but it won't be too onerous. It's just a metal, basically. Return self.metal. And we'll make it an empty tuple. I think it would be fine if it were an int instead, but a singleton tuple is fine too. Self.metal. And in room, we just have objects, right? Okay. So now in our search, we can say, where is search? Here. Visited equals an empty set, please. Oops, visited equals this. If next in visited, continue. Otherwise, visited. How do you add to a list? Append? Visited Python list add? No, not list. Python set add. Add number to set. Okay, remember. Oh yeah, it's just add. Okay, good. Visited.add of next. Okay, that should simplify our search a bit. Run it. Tuple object has no attribute hash. Ugh. That's what happens when you copy and paste the same text into 4 places. Is it's wrong once and you got to fix it 4 times. Software engineering implemented wrong. Chip instance has no attribute. RTG key? What? What? Oh. Wait, I'm a little surprised that that's... I guess this underscore is like a special thing. That means like it's scoped to the actual class name you're in. Did not realize that. Okay. But it does point out that I made a mistake by comparing RTGs and chips as if they were the same, which actually would have been incorrect. I would have said that a chip and an RTG with the same name are the same object, which would have been incorrect. So I guess you have to do like the same. You have to like check whether they're the same type. Yes. Return type of self equals type of other, and all right, so now we got some more text to copy everywhere. That's what I get for doing it. I don't know. I guess I'm not sure exactly how I was supposed to have prevented myself from running into this problem. Aside from just knowing what the right thing to do was the first time, which I don't think is a fair expectation to have. What? Why are you mad about this? The type of self is what? So we're clearly inside of chip or perhaps RTG. I don't understand where, like, we're even running into this issue. Where is this underscore? All right, let's see what double underscore means in Python. Python double underscore. Like, does it mean a special thing? Where is this RTG coming from? It has a specific meaning to the interpreter. Yes, that's what I thought. But what is the meaning? In the let's see. You guys can read this too. Why not? In the interpreter, the underscore. Yeah, okay, don't care about that. As a name. Yep. Single underscore before a name. Just is a convention that says you. Okay, double underscore means they get mangled to avoid name clashes. Fine. Underscore with at least one leading and at most one trailing is replaced. Fine. Double underscore before and after are just special method names. Fine. All right. So what I don't understand is why we are actually comparing the keys of these things. I assume that the type up check should have failed, right? Let's print self other. Try again. No, so we must be inside of RTG, right? We're in eq, right? Yeah. I wish it would tell me what method. Oh, actually, it does say what line. Line 34. Yeah, that's this one. Print self and other. An RTG and a chip. What? I'm sure Python has short circuiting. False and 1 over 0. False. Of course. What? So why are we getting into a case where self and other are of different types, and yet we still do this dumb thing? Okay, let's type of self not equal type of other, return false. False. Otherwise, return this. Okay. So we're actually, the two types are equal to each other? How is that even possible? Self is an RTG and other is a Thulian, or is a chip, right? type of 5. Type of 5 equals type of false. No, it's not. They're not equal. Why are they equal for RTGs and chips? Type of RTG of A equals, let's make this a tuple. Type of chip of A. Type instance? What? Okay. Python compare object types. I'm sure you can use isInstance, but that's not symmetric. Okay. I really don't like isInstance here. But okay, I'll just, when in Rome. Type. Let's see, isInstance takes an object, so we'll say other. RTG. And oh, not two ands, please. Oh, was that one? We got it wrong. That one was the chip one. All right, well, whatever. And this one should read chip. And we don't really need to worry about doing the same thing for room because we're never storing rooms in the same map as anything else, really. Unhashable type list. Gosh, dang it. Line 134. It's so much work to just make my data into data instead of being a bunch of objects. Ugh. All right, what is self.key? Self.rooms. Okay, fine. Well, take that. I'm making it a tuple. Okay, none type is not callable on line 88. Did I forget a return statement somewhere? That's what none type is not callable usually means. Oh, well, we can remove this, I suppose. No, that's not totally clear what's going on to me. Line 88 in hash. Line 134 in hash. What exactly are we, This seems okay. Tuple of 1, 2, 3. Yeah, it makes a tuple, all right. What is it that we're trying to call? I don't understand. Like, is it underscore underscore key? We can remove this as well. So we're in hash. And we're calling self.underscore key. And its hash is calling into the hash on line 88. Self.objects apparently has become null here somehow, which is not what I wanted. That does actually, I don't know. But let's return tuple of this. Set? Are sets hashable? I don't actually know. Let's return a tuple. That's a little bit worrying, actually, because then two rooms that have the same objects in different order might count as different. Okay, well. So we did the thing that seemed like it might help of implementing duplicate detection. But it didn't. Let's try putting a max size on our queue. We probably shouldn't have more than like 10,000 states to explore at once, right? That would probably be a problem. It would be an indication that we're incorrectly exploring the space. Python queue, priority queue. How do you do that? I remember there's you just pass max size to the constructor, but I don't remember how you later deal with that. Okay, so we pass it max size. Priority queue of max size equals, let's say, 10,000. But instead of calling add, we need to like call something else. Item block. If it raises an exception. So we need to put an item, pass false as whether we want to block what is the, yeah, okay. So let's just, oh, whoops, not this one. Okay. Oh, put no weight, in fact, is a method that exists. Okay. Well, it's good that we have not immediately hit that case, I think. Maybe we can add some more information to search output to make me believe, yeah, it ran out. Okay. Without printing the full path is sort of overwhelming, and it's not clear what to do with that information. But if we were to write, say, let's say iterations equals 0 as well. And in here, we'll write iterations equals iterations plus 1. And if iterations mod 500 equals 0, then let's print some information. Print what? Moved %d so far, currently about %d from goal. Spent cost, estimated cost. After %s, let's say. And we'll also pass in the path. How are we doing? Moved. Oh, it's going too fast. Our heuristic is like constantly 24. Is that right? Okay, stop. Printing a path was counterproductive. So let's just make it empty or something and then try again, because I couldn't keep up with it. About 22, 24. So our heuristic is not making a lot of progress. Huh. Weird. I also don't understand why it's like testing out 9 and 27, and then like it has to go all the way back to 17 and 25. Like that's quite a bit of backwards progress. Kind of weird. Well, let's switch this to like 5,000 and actually print the path and see if maybe maybe looking at the paths gives us any help at all. Probably not though, right? Whoa, that's a lot of moves. It's basically just moving strontium and ruthenium up and down on floor 3 for some reason. But here's the thing, like, let's actually like go back to like just mod 1, which is always going to be 0, and pipe this to like head 40 or something, right? So we're actually getting substantially closer to our goal for a while, right? We moved 3. We moved the plutonium and the strontium upstairs. And then we moved the plutonium together with its thing upstairs again. And then we're bringing the promethium and the plutonium back downstairs. No. We're moving them upstairs to floor 3. Promethium and plutonium chips are upstairs. Okay, so I'm starting to get the impression that our heuristic might be inadmissible somehow. Well, but if it were inadmissible, that would mean it's sometimes overestimating. That could cause us to explore the wrong paths, but it shouldn't make us, like, I don't know, Shouldn't, I would think, make us never explore the correct path. It'd make it take longer. Well, let's go revisit the heuristic for a bit. Our goal estimate was for each object in the room, except for one of them, it's going to take you at least 2 moves to get it upstairs. Or twice the distance from here to the top floor. Because you'll have to move move pairs of items upstairs, but then still come back downstairs with a single item. So you've only actually made enough progress to move one of them upstairs. So assume you have to move all but one of them, and maybe the other one is like fine to have because it simplifies something else. That seems okay, honestly. I mean, I could remove the limit and just let it run like overnight. I don't think that's really the thing to do. And I think it'll probably run out of memory overnight as well. I was just doing a spot check here that I spelled all the metals right. That was something I said I was going to do before, but actually didn't. So it seems like we're actually like doing the right things. We're just not getting an answer. All right, let's remove all this printing, I guess. Well, maybe not remove so much as comment out. Oh, whoops, I forgot. We actually have 3 lines here to comment. And let's get rid of the queue max size as well. Who knows, maybe you need 10,000 things open at once. Not sure what to investigate next. Again, we could set our heuristic to just always be 0, but we tried that a while ago. And it's going to make things a lot slower because it won't be a directed search at all. We'll just basically try all possible moves. And I don't think our heuristic is the problem. Actually, maybe a problem is just that we don't recognize when the problem is solved. That would cause some issues, wouldn't it? So let's write, say, node of list of, let's say, nothing, and 0 dot evaluate. Succeed. All right. Well, room empty list. That also succeeds. Chip. Okay, let's make a 2-floor thing here. And on the bottom floor, put a chip of X. That is progress. And if we move the chip upstairs, it succeeds. So that doesn't seem to be the problem. Oh, wait. No. I was thinking briefly that, like, that we would have some issues if all the objects being upstairs causes them to break, right? But well, let's double check that. RTG of X. That's still a succeed. RTG of Y. That's a succeed too. All right, that's. I guess we should never run into that case, but we should probably flip these two conditions. If any room is illegal, we should fail, even if somehow it's the case that all the objects are on the top floor. We're correctly handling the elevator moving around. As we saw earlier when we were looking at the output of these processes, they were, this one was moving plutonium and strontium upstairs, and then moving the plutonium and its chip upstairs, and then moving the promethium and plutonium chips upstairs, then moving the plutonium chip back downstairs. I'm not sure exactly why it's doing that, but it is moving it onto a floor with its RTG, so that's fine. I guess it just needed to take something back downstairs in order to use the elevator again, right? So, like, these searches seem fine. It's exploring things that seem like reasonable approaches, but so our duplicate detection is not perfect because we're tupling up the items in a room, which makes them order dependent. But is that relevant? Yeah, it probably is, actually. Maybe we could improve that. Where's room? Room is this one. But we need two equal objects to hash the same. So we can't just improve equals and leave hash alone. We need a better sort key. Right? Like this. Sure. Let's try running it with that little improvement. But of course it's not going to make a lot more progress. So, what are we missing here? It seems like A* should be a good algorithm for doing this. We have a search space. We have some way to estimate how close we are to the end, even if we're not even if it's not a great estimate. So it does seem like A* is a fine algorithm. What's going wrong with our implementation? What's our branching factor look like? Well, I mean, how many objects exist in the entire world? 1, 2, 3, 4. There are 10 objects in the whole world. So at the absolute worst case, our branching factor is all 10 objects are on the same floor. And then there are 180 moves we could make. That's a pretty high branching factor, right? We could move any one object or any two objects, either upstairs or downstairs. But the thing is, a lot of those moves will quickly be ruled out as illegal because we'll move like a chip. We'll move a generator away from its chip or something like that, right? So most of those moves are illegal in a lot of cases. And furthermore, you won't typically have all 10 objects in the same room. It seems like in practice, our branching factor is going to be like, oh, there's probably about 3 objects in a room, so like there are 12 moves you could make, and several of them will be illegal, so call it like 5. And a branching factor of 5 is perfectly reasonable, I think. I mean, A star classically is often used to search grids, like actual spatial grids where you can move north, south, east, west. And the branching factor there is 4, so that seems fine. How many moves is it going to take to completely solve this? Well, our heuristic is 28. We know it's going to take at least 28. Great. Oh, look, it's done. We made 31 moves. Oh, geez, good. I was worried we were going to have to take another break. Let me put this into the puzzle thing and see how it goes. Minimum number of steps is 31. That's the right answer. Okay, thank God. I was going crazy. All right. What's the second question? Oh, good. They added more. Oh, here. Let me show you guys. This is how I show you guys. You step into the thing. You notice there are some extra parts on the first floor that weren't listed. Fine. So we can do this pretty simply and just say, well, let's just edit it in place, right? There's nothing important to preserve about being able to solve both parts at once. The first floor just has 2 more things. Right, why did it... why is this not indent right? X? Then it does, okay. RTG of... They were Elerium and... It doesn't really matter, right? Elerium... RTG of dilithium... and RTG... No. Chip of dilithium... I'm surprised that we got up to more than 10,000 objects in our queue, but we're actually still making good progress. Okay, so let's put this stuff back in at like 5,000, but without the path. And let's also not even print the path anymore. Let's just call search. Oh, we can get rid of this int search node. Search root of 0, I believe, is the... What are we returning? New cost, new path. Yes, okay. So this should take a while. In fact, let's time it. Here you go. Run in the background. I got some Git work to do. Where were we? Okay, I never even actually added any of this. Day 11, parts 1 and 2. I guess that I a number of times I thought to myself, you know what, I should commit this, and I just sort of like never got around to doing it, and so instead we committed it all at once. Oh well. So how much harder has this made the problem? It doesn't seem like it should take that much longer. I also don't know how much of the stuff that we did was actually necessary. But the good news is we should be able to reuse a fair bit of this code in some future problems that involve search. I overheard, I don't know how true it is, but I heard someone saying that day 13 is just a rehash of day 11. Well, we have a great solution to day 11, I think, in that we have a general A-star search algorithm. And maybe this will be a good time to learn how Python does libraries. How can I define my own A-star search library and reuse it across multiple problems rather than just copy-pasting it? I could just copy-paste it, but one thing is it was a tremendous amount of work to just like create a set of objects, right? That was a ton of work. It took me like 20 minutes to make all of the objects I defined become suitable for being put into a set. When like if I had just used tuples for everything, tuples everywhere, tuples and functions instead of classes and methods, it all would have just been like automatically for free. But I would have had to deal with like tuple soup, which, I mean, maybe you haven't heard the term before, and I don't know if I have either. Maybe I made it up, maybe I copied it, but I think it's pretty clear what it means. It's just like, what's your data structure? Oh, it's a tuple of 5 tuples where the first element is a tuple of 3 tuples. Stuff like that, and it just becomes quickly unmanageable. It's a shame that we have to choose between having data types that work well by default and having data types with like features. I don't know. In both Clojure or Haskell, it would not be hard to put objects of our own custom types, or putting objects that are in the way that language prefers you to represent things into a set. Because both of those languages focus on immutability, and therefore there's like, it's fine to just implement hash by default for everyone in a good way, as opposed to just using in an equality-based way instead of an identity-based way. Because object identity is not relevant if nothing ever mutates. You might as well just use equality. And so the language. So Python could provide for you a default hash and eq method that does basically what we're doing. And then people using classes immutably would be in fine shape and wouldn't have to do any work. I'm not saying that's what Python should do, because if it did, then when you use mutable objects, you could accidentally make one a hash key without thinking about the repercussions, and then when you mutate it, it would be like really sad. And so Python takes the approach of saying, look, if you want to make these things hash keys, you have to make it very clear that you're never going to change them. But what that means is that whenever you want to deal with like immutable, stateless class things, the language is just fighting you the whole way. And it's like, is it really that outrageous to want to put an object into a set? It doesn't seem that outrageous to me. I feel like there must be a lot of optimizations that we're missing. Because I don't think this is supposed to take very long. Like, I'm pretty sure I saw posts on the Reddit here. What are you guys even looking at? You're still looking at the advent of code. All right. I couldn't remember. I feel like I saw posts on the Reddit of a guy who was like, here's my solution that uses some optimizations and figures out the answer in 1/10 of a second. And like, I'm pretty sure this is taking us longer than that. Like, I haven't been counting closely, but I'm sure it's been at least 1/10 of a second. I wish I had timed the previous call. I wonder, actually, if we've made things very expensive by tracking the path we're taking, right? I'm just so used to it being cheap to add lists together. It didn't occur to me that in Python, a language where lists are mutable, that creating a copy of a list is very expensive. Copying a list and adding one thing to it to get a new list with more stuff is like super expensive. I'm used to that just being real cheap. So maybe the problem is that we've made the problem quadratic where it didn't have to be by tracking the paths because I thought I might need them and it was cheap to make them. But actually it's not cheap at all. I'm actually going to cancel that running thing and get rid of the path because I think that is pretty expensive. So let's just throw away this path stuff. Everything that says path, we're throwing away. Now, this means that let's see this. This means that our A* algorithm no longer works if you want to know how to get somewhere. Fortunately, we already committed the previous version. So if we need it back, we can get it back. Need more values, node.next. Yeah. So if we need to get back the version that actually gives you a path, we can take it. But it'll need some work. We might have to implement cons cells ourselves, which is a little bit silly. But it's so if you don't have a background in functional programming, you may say, how can it be so cheap to add things to a list? Well, if you're guaranteed that list items never change, and you have a list 1, 2, 3, you can use a linked list, is like a standard thing to do in functional programming. And it's a singly linked list where you can just get that stuff from the front. So it's very cheap to add an item to the front of a list and get back a new list. You just add another node at the front that says 0, and you point it at the previous list that says 1, 2, 3. And that's fine since you're guaranteed that the previous list will never change. Likewise, it's very cheap to remove in quotes, the first item in a list and get back a new list with one fewer item. Making changes to the back end of a list is much more expensive because you have to do a bunch of copying of things to change the next pointers. But you can generally arrange things so that you only work with the front anyway. In Python, this would probably mean creating our path backwards, and then only at the end, when we finally have our solution, would we reverse it. So that's a thing we could do if we needed to get the paths back. We could implement cons cells, basically. And that's what those are called. Linked lists, singly linked lists where you have a value and a next. If you are from a functional background, you're sort of used to calling those cons cells for historical reasons. The name really doesn't make any sense anymore, but it's been around for 40, 50 years or something, and so everyone still uses it. how old is Lisp? I don't know, 70s, 60s, something like that. You know, I'm just going to leave this one to run overnight. I got to get some sleep. This episode's gone on for a while, and we know that our algorithm is correct, even if it's not nearly as fast as it should be. So I'm just going to leave you guys in suspense as to how long it takes and what the final answer is. Sorry. But I got to go to sleep, and I don't know how long this is going to take. And we've done all the interesting stuff, including a fair bit of perhaps uninteresting exposition by me. But I think we're basically done with this problem. Anyway, thanks for watching. If you guys sat through all, what was this, 4 episodes or something, good on you. That must have been grueling. I'm glad you enjoyed it. And if you're here and you didn't enjoy it, man, I feel sorry for you. Thanks for watching, and I'll see you next time.